The concept of this video is to present two very complex ideas. The ergodic hypothesis studied the stochastic random processes measuring peak-to-peak and RMS of a random signal, the addition of two random signals, and a review of sweep frequencies. Here are the two circuits. Actually three. One creates the noise, and these two are in parallel, added together, creating a third RMS noise, which is typically 40 RMS. Here's a typical RMS signal. On this circuit, you get variations, of course. RMS is typically around 40, and the peak-to-peak is around 240. The sweep is about 50 microseconds, and the higher frequencies go up to about 10 kHz. Any event, all noise frequency is random, but they have regular properties. That is the RMS, average energy, and the peak-to-peak. You cannot predict where any signal will be, but an overall envelope. Let me see if I'll restart this. Here's another sweep. And of course, the RMS has changed and the peak-to-peak. Now I'll set it to run to get an idea of what this looks like. This again is truly random. It's noise. Noise is the front end of the first op amp and then amplified by 10,000. I'll now show you a slow sweep. Here's a slow sweep rate of 20 milliseconds. Note the RMS settles down to around 40 with variation. Peak to peak runs about 240. Each individual circuit that creates this and is added is about 30 volts RMS, or 30 counts RMS. Peak to peak is 0.24 volts, given the scale 50 millivolts. The concept of ergodic says that if we take 100 of these noise sources in parallel and take a snapshot of them, we will get an RMS and a peak-to-peak. If we took just one of those oscillators and created a time series, the RMS and peak-to-peak would be the same. This is an ensemble measurement versus a time series. The ergodic hypothesis says that they will be the same, or a belief in statistical mechanics. No presentation can really grasp all of this. There's a lot of math, and I won't attempt to present that part of it.